Hello and welcome back to Let's Code Physics. We have had some success transforming our wave function evolver to run in 2 dimensions. So what that means when you have 2 dimensions is that you can have one particle moving in 2 directions. So you can have a single particle moving in the x direction and in the y direction. Or it means you can have 2 particles moving along 1 dimension. So when we say that a problem is 2-dimensional, we mean that either it's a single particle in what we usually consider to be 2 dimensions, or it's 2 particles in what we usually consider to be 1 dimension. And that's what I'd like to extend the code to look at next. So imagine that we've got a red particle somewhere along an x-axis, basically. And then imagine that we've got an identical green particle, but we're painting them different colors so that we can tell them apart. And let's suppose these 2 particles are charged. So let's say they're both electrons, maybe. So if that were the case, you'd be interested in the distance between them. Good girl, Pumpkin, you're very strong, and I'm very impressed with you, and I love how you want to show to the internet how strong you are. So we'd be interested in the distance between them, which we might call r. That's not a very good r. There we go. There we go. That's a little bit better handwriting. And what you'd be interested in if these were electrons, let's suppose each one of these is an electron. So electrons carry this negative charge. So they are going to tend to repel each other. And so that repulsive force means that they're going to experience a potential energy that's equal to a constant times each of their charges, Q1, Q2, divided by their distance. So if the 2 charges have the same sign, meaning this is positive and this is positive, or this is negative and this is negative, then the potential energy is going to be positive, and it's going to be increasing as you approach r equals 0. So as they get closer, the potential energy is going to be increasing. Things tend to roll downhill, so they're going to tend to roll away from each other. If I made one a proton and the other an electron, then this would be a net negative, right? So you'd have a positive times a negative, or a negative times a positive. This whole thing would be negative, and so they would tend to roll toward each other. And so if I wanted to set this up in the code, I would need to put this in for my potential energy. And the way I would do that is I would keep track of each of their coordinates. So I'm going to call the red one's coordinate x, and the green one's coordinate y. If that gets confusing, just think of it as an x1 and an x2. It doesn't really matter what you call them. The reason I'm calling them x and y, honestly, is because I already have the code in terms of x and y. So rather than replace all of those x's and y's with x1s and x2s, I can just do it this way. It's a lot easier. And so basically that would mean that my r would equal the absolute value of x minus y. And we're putting in an absolute value because it doesn't really make sense for it to suddenly become negative just because one is on the other side of the other one. So this potential energy in the code is going to be K Q1 Q2 divided by absolute value of x minus y. And the beautiful thing about absolute value is it doesn't matter whether you call it x minus y or y minus x, because it's the same thing. So let's go over to the code. So what I've done is I've set up 2 graphs now for the expectation value. They'll be on the same graph, just 2 different plots. One's going to be colored red, the other one's going to be colored green. So we're doing the red-green show today. So the red one is going to be the one labeled x, green is going to be the one labeled y, just like I drew in here in the picture at the beginning. So let's scroll down here. We are still having a pretty blockish grid. It's not terribly smooth, again, just to keep it running decently. So what I've got here is I've got the K, Q1, Q2. I actually have a mistake here where I made this a negative, so I was testing actually attractive potential energy earlier, so I made a little mistake there. And what happens is if x is equal to y, which is going to diagonal of this grid, x is equal to y, and so every time it hits that diagonal, it's going to get a 1 divided by 0, which causes the program to stop because it's made by mathematicians. They don't want 1 divided by 0 to be infinity. And even if it were infinite, a computer doesn't know what to do with infinity. So we're going to make this actually the minimum of the potential energy, or 500. So if you imagine we're taking this potential energy that looks like this. So here's R. Here's the potential energy. So it's taking this potential energy that looks like this, and it's saying, you've got a maximum value, so everything up here is erased, and you're just going to flatten out right here. And that's just to avoid this thing climbing up toward infinity, so we're just picking a number. I picked 500 arbitrarily. We could change it later to see if it makes a difference, but it's ridiculously high. And I've made these both electrons, even though it doesn't really matter, because negative times negative, same thing as a positive times a positive, although I did need to remove that negative, because I guess I was thinking of the gravitational force earlier, although I was apparently putting a negative mass, but the code ran, so that's what counts. Again, we're taking a little precaution so that we're only setting up the initial wave function within this range, but we're going to stick with our displaced Gaussian. So we've got this Gaussian, the two particles are starting off like this. Let's actually have one of them displaced along the axis and the other one not displaced. So I can't think of this necessarily as an x-axis and y-axis anymore. I have to think of them as the particle 1 axis, that's going to be along the horizontal, and the particle 2 axis is going to be along the vertical. So when you see this Gaussian peak, it doesn't mean that there is a particle at that location. It means that that's the probability distribution of think of it as like the joint location of the two particles, of the location of particle 1 and the location of particle 2, even though they're really along the same line. I think that's where the expectation value graph is going to be helpful. Let's see. Let's get rid of that because I have fixed the issue, it seems like. Yeah, let's just go ahead and leave that like that. That doesn't oh dear. Let's actually put this back in the way it was. Just so that way they're both ascending. Causes a problem. I'll go back and change it. Oops. Wrong button. Key, excuse me. Let's see, we've got our dot list there. So down here is where we're evaluating the expectation value. So again, it's just an integral. It's just a summation of the x value or the y value times psi modulus squared. So you notice psi is evaluated at the particular x and y value that you're looking at, but x and y kind of get stuck, right? So x is not a function of y is not a function of x. You multiply by dx and dy, and then it'll add to the graph expectation value of x and expectation value of y. And then it does the same thing down below in the loop. Oh, I did do one thing different to help us visualize it. I promised this last time, and I've set it up. I skipped right past it. I was looking for it and then skipped right past it. I've set it here where it creates the dot list that the color of everything is going to be white unless we're at the midpoint of the x values, that corresponds to the y-axis, or we're at the midpoint of the x values, that corresponds to the horizontal axis. And what that means is that the vertical axis is going to be colored green, right, because that's the location of our green particle, and the horizontal axis is going to be colored red, because that's the location of our red particle. So when you see the peak in the animation, the peak's location along the red indicates the location of particle 1, and the peak's location along the green indicates the expectation value of the location of particle 2. A lot of modifiers in that sentence. Boy, quantum mechanics leads to some very complicated sentences. It's because we live in a classical world and we're trying to describe quantum effects. If we lived in a quantum world and we're trying to describe classical effects, I don't know whether our sentences would get more or less complicated. That would be an interesting philosophy exercise or something. So anyway, we're going through the same process. We're graphing expectation value of the first one, expectation value of the second one's position. So let me get this. I'm going to get this started just to show you how it works. And then what I'm going to do is I'm going to cut, and I'm going to have this thing record overnight, because you saw last time this thing moves very slowly. So I'm going to have this thing record overnight, and then I'll come back and record some commentary over it with the video sped up by like a factor of 100 or 1,000, however fast I can get Windows Movie Maker to move it. So let's run this and make sure that it, oh dear, a division by 0. It did not seem to have that problem before. Okay, what did I change that caused it to have a problem? Maybe I should not have changed this back. Maybe that actually, does it, that shouldn't prevent it, I would think, but let's see. Alt 3, 5. Okay, apparently that fixes it. You know what? I'm not going to argue with it. Okay, well, I won't argue with that. Although, the fact that this is negative, should that be negative? Where's the peak located? All right, so here's our Gaussian. You can see it's kind of getting broken up along the diagonal because that's where x is equal to y, so that's where the particles are not allowed to be near each other by the repulsion. So red, where is this peak located? Suppose the peak is located over to the left. How did I set up that initial wave function? Minimum of this with that. Okay, right. Good. Oops, that'll be down here. No, I didn't displace the x. So why is x's expectation value, why does it start out non-zero? That's a bit weird. Because I would expect this thing to be centered along the x. Okay, well, I tell you what, let's actually do this. Now I'm worried that this thing has messed things up. So let's take this out. That shouldn't be making a difference. Oh, except that my dx is now negative. Oh, that's why it's recording that as a negative, because my dx is now negative. I need to, okay, what I actually need to do is, that should be affecting the y as well, shouldn't it? Because I'm thinking is when I multiply by the dx, I'm treating dx like a negative quantity now. So actually, let's put this back on. Yes. So comment that out. Uncomment this. All right, that's going to throw a division by 0 problem, which I wasn't getting before for some reason. So this ordering has somehow thrown off the the looping somehow. But let's just let's go back up to U, and here's what we'll do: is we'll say if x is equal to y. I don't know why I put parentheses around that. If x is equal to y, then we'll just have u equal to its cutoff value of 500. Else u is equal to the minimum of these two. I do want that to be the minimum, right? Yeah. Okay, let's try that. Oh, cool. All right, okay, so these are both positive now like I expected. Okay, so that was throwing it off. That I wonder what that did to my results in the last video. Well, I've already recorded that one, and you've already seen it, so we're not going to worry about that. Okay, so everything is working fine now. So what I'm going to do is I'm going to step away. I'm going to let this thing record overnight, and then speed the video up and provide some commentary. So I will be talking to you in just a second. All right, so here is the simulation, sped up 64 times, so that instead of it taking 10 hours, it'll take just under 10 minutes. One of the things you notice that happens right away is the two-dimensional waveform splits into those two quadrants, quadrant 2 and quadrant 4. So those basically indicate that those are where the two particles are at opposite ends of the mesh. You don't see a whole lot of wave function going on in quadrant 1 or quadrant 3, the upper right or the lower left, because that would indicate that the two particles had a high probability of being on the same side of the grid. Because you remember the green axis indicates the probability of where you'll find the green particle. The red axis indicates the probability of where you'll find the red particle. So the fact that these two are centered in those two quadrants indicates that the particles are going to tend to stay away from each other. That's what we'd expect. since these are particles of like charges. You can also see that in the expectation value graph, the expectation value at the position of the green particle, expectation value at the position of the red particle expectation value quickly descends down to the negative region to be on the opposite side from the green particle expectation value. So even though there's this split down the particle 1x equals particle 2x location there in the waveform, there is some weight shifting back and forth between them. So there's been enough weight shifted over from one side to the other to give you these expectation values. Although you do see the red expectation value creeping up towards 0 a little bit, you also see that it's kind of moving almost in sync with the green particle's expectation value, so that the distance between them after settling out remains pretty constant, which is an interesting result. And of course, as soon as I said that, the red one took a dip that the green one did not take. But yeah, so what you notice that in the wave function animation, there's this gulf along the what looks like the y equals x line, because it's very low probability for the two particles to be at the same location or at similar locations. And so that's sort of like got this valley running across it there. Earlier, the two peaks were kind of well defined. Now they're kind of spreading out a bit, so we're getting a little bit more standard deviation in there, which I did not calculate. That's only got the expectation values on there. But again, you notice that the two expectation values are kind of tracking with each other. They're maintaining roughly an equal distance because the particles, they're bouncing off the infinite wall at the edge of the region, but then of course they're being repelled by each other. So yeah, like I said, this thing took 10 hours to run, so this is being sped up 64 times. This thing ran overnight while I was sleeping. Now the red curve here, the red expectation value is actually getting close to 0. It's getting close to the midpoint of the region, indicating that there's sort of equal weight across the red axis between the two regions there. The green one, on the other hand, definitely staying on the positive side. So you can see that the upper left peak in the white wave function is pretty definitively higher than the lower right peak. I think there's actually, if I remember looking over the graph, if I remember correctly, there's actually a point at which the red one does cross 0. But again, you know, as the red one's getting closer to 0, the green one is getting closer to the right boundary, to sort of that upper limit there. And of course, these two are both favoring being more positive than negative because I centered the Gaussian, that initial wave function, just off center, so just away from the origin. You notice in the first part, I didn't even have time to comment on it. It moved so quickly on the sped up version that it pretty quickly split in two as those two expectation values began to decline. Oh, look, I think here is where we get okay, we got a little blip of the red particle expectation value above 0, above the halfway point. So it's still weighted a bit to the right of the region, if you will. The interesting scenario to try to get, and I don't know that I have time to try a whole lot of scenarios on this. I would like to get on to some other potential energies. The interesting scenario to try to get would be to try to see if you could ever get the red and the green curves to cross. Basically, you would have to give the particles a lot of kinetic energy to try to make it past each other. And of course, this is there is a little bit of artificiality to this, not just from the finite difference approximation, but also from the fact that I had to put a cap on the potential energy. So when these two get close enough together, they see a constant potential energy, not an infinitely high potential energy. Because remember, we set that to be a flat value when they reach a certain distance from each other, just to keep the code from making itself explode. Here they're actually getting pretty close. The red particle expectation value is staying pretty steadily above 0, so they're both definitely in the right half, and you can see that in the wave function animation, the peaks have now gotten closer together. So they've bounced back off of the infinitely high walls enough to overcome some of the repulsion that they have toward each other. And now that that repulsion is set in, now they're racing back, or at least the red particle is racing away from the green one. Oh, there the green one goes, racing back the other way. So this is kind of a cool view, getting to see the expectation value evolve along with the two-dimensional wave function. Okay, so the red one is definitely bounced back over to the left side now. And again, the two peaks have moved apart from each other. So the peak distance, I guess, roughly equates to the distance between the expectation values is one way to think about that. Let's see. There's not a whole lot of interesting stuff happening to the waveform in and of itself. Obviously, it's breaking up into some constituent, waveforms, but they're basically maintaining their peak-like shape. Gaussians tend to be pretty well behaved in a quantum mechanics problem, even when they are obviously not Gaussian. I mean, these are obviously not Gaussians. They've got multiple peaks. They're asymmetric, but they still stay, nicely well confined, well localized. I guess that's the word I'm looking for. But again, there is not a whole lot happening in quadrants 1 and 3. There's a little bit of leakage into those quadrants. You see a little bit of you see some peaks up near the very top and bottom of the green axis and the left and right of the red axis. But like I said, along the x1 equals x2 line, there's not a whole lot going on. It's sort of eating up all the waves that come its way. Oh, red is coming back again. It looks like. Again, the two expectation values, they're keeping a relatively constant distance in between each other, so that's interesting. Which is kind of what you would expect, right? So you would expect this thing to try to reach, some sort of equilibrium. So you can imagine this at play when you've got many, many electrons in a conductor where the electrons are free to move around. They're going to tend to move to wherever they can be as far away from each other as possible to a consistent distance. And that's why we say that all the charge on a conductor moves out to the surface, because they're going to be repelled from each other, and that's as far away as they can get from each other. I would love to be able to simulate that, but this is 2 electrons in a 1-dimensional geometry, not billions of electrons in a 3-dimensional geometry. That was going to require significantly more computing power than my little Acer laptop can muster. Yeah, so the red expectation value still climbing, it looks like, above 0. And you take a look at the wave function pattern, it's looking really interesting. We've got almost these 4 little bands there, and the 2 in the middle there, they're approaching the x1 equal x2 line, or getting higher. Now they're getting scattered a little bit more. It's actually almost looking flat. I wish I could